let us continue. The next speaker today is Professor Gusein-Zade. He speaks about Alexander polynomials, their generalization and topology algebraic links in some rational homologous field. Please.
Okay, thank you very much. I want to express my deep gratitude to the organizers for giving me a possibility to participate in this conference and to give a talk here. And my talk will be mostly about knots, which seem to be, as understood here, less interesting for those who are interested in volumes of hyperbolic manifolds and so on. Namely, these are algebraic links. Algebraic links means the following. So the algebraic link in the 3-sphere is defined by the following. Let us consider in the plane C2, in the neighborhood of 0, that is at the gem C2 0, let us consider an algebraic curve C0 in the neighborhood of 0. And let us take the intersection of the curve C, complex curve, with a small 3-dimensional sphere around the origin in C2. So this is the sphere here. So the result is link in S3, in this S3, like that. And then the link, the result is not a link or not. This depends on the properties of the curve. If the curve is irreducible, you get a knot. If the curve is irreducible, you get a link with the number of components equal to the number of components of C. Now, for example, for the simplest curve, x squared plus y cubed equal to 0, one gets the threefold, of course. So the intersection of the sphere, in this case, epsilon, can be taken. Arbitrary one, and this is threefold. So some statement about invariance of algebraic knots and links. So if you have a knot in S3, even a link, excuse me. If you have a link in S3, which is a union of reducible union of some components, linked knots for I from 1 to R. Then one can define the Alexander polynomial. So if you have a knot, Alexander polynomial is a polynomial in one variable. If you get a link, you can of course also consider polynomial Alexander polynomial in one variable, but there is also Alexander polynomial in several variables, the number of variables being the number of components. So you get delta of T1, etc., TR of R variables, which is the Alexander polynomial of this.
Does it exist non-algebraic links? Algebraic?
Algebraic links, yes. But Alexander polynomial, of course, is defined for all.
No. There is a link which is not algebraic.
Of course. So for example, this 8 knot is not algebraic. Algebraic knots are somewhat specific ones. Namely, all of them are toric knots. So, iterated toric knots, not of course toric knots. Iterated toric knots. No, in links are more or less similar. So there are strong restrictions. Moreover, not all iterated toric knots are algebraic, as you will see in a minute. So the statement is the following: that for algebraic links with R components, the Alexander polynomial completely determines the topology of the link. So this is the unique invariant. There is nothing more. In particular, for example, I told you that one algebraic knot is the threefold. However, there are two threefolds, of course. And one can, because of my statement in particular, but one can understand that the threefold, one of them is algebraic and the other one is not. And in fact, the algebraic is this one, just for this was in fact determined. So the picture, the corresponding computations were made by discussing with Binnikov, and he produced the corresponding picture. This is the algebraic threefold, and the other one is not. Okay, so now let us move. So this is in some sense this in S3. This is the statement about the Alexander polynomial belongs to certain Yamamoto. I don't remember precisely the date, but it doesn't matter. And let us move to algebraic knots in other three manifolds, which are first, which are homologous sphere, and then to some rational homologous sphere. So the rational sphere is good in the following sense: that suppose you have a homologous sphere. Suppose you consider a homologous sphere. So I didn't think how to denote it. Well, let it be K. Okay. So suppose this is a homologous sphere, a manifold, three-dimensional manifold. And in this case, any link or knot that is linked with one component in it can be, so has the same invariant. The Alexander polynomial, the definition of the Alexander polynomial, at least one of the definitions, can be applied not only for knots, links in the standard sphere, but in the homologous sphere. There is no difference. You can take the complement, take the corresponding abelian covering, look at the shift map, and the determinant of it, the homologous corresponding. So, what sort of homologous spheres and later rational homologous spheres we shall consider part of them? So, suppose now that you have, let it be just to distinguish S, which I will use in a moment. Let us consider a certain surface. Instead of C2, we now consider a surface S0, two-dimensional complex surface with a singularity at one point, and we consider it as a gem in the neighborhood of this point. And suppose again, so then if the surface is has so-called rational singularity, I don't want to make the details because I'll consider particular rational singularity. Because of that, I don't want to discuss the general definition, general statement. But in this case, if you take the intersection of S, so suppose this is in Cn, we embedded in Cn0, and can be large enough. And if you take the intersection of S with the sphere of dimension 2n-1 centered at the origin here, you will get three manifold, of course. So S is complex surface, it has dimension 4, real dimension 4. If you intersect with the sphere, you have three-dimensional manifold, and it is this manifold is a rational homologous sphere. However, there is one case when it is not rational homologous sphere, but simply homologous sphere. And this case was just mentioned by Sasha Mednych. And this is the case when S has this so-called E8 singularity. So suppose that S is given, so S0 is inside C30 hypothesis singularity. And it is given by the equation x in the power of 5 plus y in the power of cube plus z squared is equal to 0. And then, if you take the intersection of this surface singularity with the sphere, you get exactly the Poincare sphere, which was mentioned that talk, and this is the homologous sphere. So it's homologous are just zeros except the dimensions, standard dimension zeros. Okay. So as I told you, in this case, one has the same invariant. I mean, the Alexander polynomial can be defined for a link in this manifold, algebraic one or not, but we shall discuss algebraic links. That is, that we take as it was defined here, we take as a curve, now not in C2, of course, but in this surface, curve C0, and we take the intersection of this curve with K, that is with that C intersected with K, will give you a link in K, in this case in the Poincare sphere, and we get. So the question which I want to discuss first, to which extent the Alexander polynomial determines the topology of this link. By the way, in order to discuss the approach to this question, I want to mention the following: how the fact that the Alexander polynomial determines an algebraic link in S3. How is this fact proved? So in fact, this fact follows from the following: that one can, if one has a curve singularity inside C20, one can make resolution of this singularity. This resolution can be made by a sequence of blow-ups. And so after that, one gets certain some components which are glued inside by these blow-ups. All of them are isomorphic to CP1. They have certain self-intersection numbers, and they are intersected with each other. And the curve, after the resolution, the curve appears to be consist of components which are transversal to this exceptional divisor. So the strict transform of the curve looks like following. So there are some components which are here, and all of them intersect components of the exceptional divisor at smooth points. That is not at exception points. This means the resolution. And the fact is that the Alexander polynomial determines completely determines the combinatorics of this resolution. One can restore it. And this, this easily implies that the curve, the topology of the curve, is determined by the Alexander polynomial. So let us discuss what is the situation with the E8 singularity. So if we want to resolve curve singularity inside this surface, inside the E8 surface, so this is called E8. Terminology of, I don't know, maybe even Turing started this terminology, or at least now it is most attributed to Arnold. then we have to do the following. Before getting a resolution of the curve itself, we have to resolve the surface. And the resolution, the standard resolution of the surface leads to the following picture of the E8 surface. The following picture. It consists of some letters. I'll draw it, but in fact it is more pleasant to draw another picture, the dual one. It consists of 8 exceptional components of the exceptional divisor: 1, 2, 3, 4, 5, 6, 7, 8. But usually, in order to describe a resolution, it is more convenient to use the dual picture, so the dual graph of the resolution. That means that to each component of the exceptional divisor, we associate a point. And if 2 components intersect, then these points should be connected by an edge. Then you get this picture means simply the following. You see, there is a chain 1, 2, 3, 4, 5, 6, 7. So you have 7 vertices 1, 2, 3, 4, 5, 6, 7 in a line. Each of them is connected with the other one because they intersect by one. And this one intersects with the additional one. So this is the picture of the E8 Coxeter diagram and so on. So in particular, by the way, another construction of the Poincare sphere can be made in the following way. One takes 8 copies of CP1 and then takes over each of them, one takes the line bundle O of -2. This means line bundle with the self-intersection -2. And then locally, you have the following picture. So if you take here a neighborhood in CP1 and here a neighborhood in the fiber, you get product of two disks, of course. But now I told that we have to take 8 copies of that, and then you have to glue them in the following way. You glue first with the second, first with the second, second with the third, third with the fourth. So this is line, and this also with this. So you take 3 points where you glue them together, and you glue in the following way. So you take here is 1 copy in this small neighborhood of this product of 2 disks, but you glue with the other one, which is here. So this is what we call the space of this bundle, and here is the space of this bundle over that one. These are dotted lines. I drew the CP1s. And then you get, no, it is topological manifold, but if you make smoothing here, just at these corners, you get the Poincare sphere. This is another construction of the Poincare sphere. And the fact that this is really the Poincare sphere in the sense, this is homology sphere, follows from the fact that if you take this matrix -2 and so etc. -2 and also 1 at the places where you have edges, means 1, 1, 1, 1 to the last place. But the last place should be connected with what? With 3. 1, 2, 3. So take this matrix and everywhere here has zeros. You get the matrix with the determinant equal to 1. This is, one can show that this is just fact. This implies that the result is the homologous sphere. By the way, if you take other Coxeter diagrams, that is, for example, AK, DK, I consider only Coxeter diagrams with vertices of the same sort. AK, DK is 6 and D7, then the corresponding matrix always has the determinant different from 1. This means that the corresponding spheres, the corresponding links, K, are not homologous spheres, but only rational homologous spheres. There are homology group. The first homology group is finite. Okay, so this is that one. And now, and then if you have a curve on this surface, then to resolve the curve itself, you have to blow up further. So on this picture, the curve the strict transform of the curve is in principle represented by some gems of curves which are singular and which can be tangent to these components or even at the intersection point. So you want to get a resolution, one needs to make additional blow-ups, singular points. Then one gets there. So now somehow a sort of a good dream would be if the Alexander polynomial of a algebraic link defined by a curve determines the resolution from combinatorial point of view completely, then of course it would imply that the Alexander polynomial determines the topology of the algebraic link. But this is in fact not the case. The situation is like the example when this does not happen is the following one. Suppose you take two, in fact, irreducible curves. This means that we get not links, but really knots in the Poincare sphere. One of them is defined by the following. It is so-called curvet at the component, let us denote component D1, D2, etc., D7. This simply names the devices. D3, and this is D8. Let us. By the way, there is another numbering, but this probably does not matter. Like in my picture, though it is not essential. And one of them, one curve is determined by the following construction. You take the so-called curvet at the component D6 at this component. This means the following, that on this picture, where the exceptional divisor is drawn, you take a curve, simply analytic curve, which is transversal to the sixth component, to this one, at a smooth point, like that. You take simply as a curve, a gem of a curve, which is transversal. And then to get a curve here in the surface, you simply blow down all this picture. Simply go back. This is resolution of that. So there is a map to this, and you get a curve here. And then this is one curve, C1. Rather, I put here the strict transform of that curve. And another curve, C2, is the following one. You take a point, smooth point at the component D8, and you take here a curve which is some sort of cusp. Some sort means not semi-cubic parabola, but locally it is defined by equation x5 plus y squared is equal to 0. So it is parabola of also semi-quintic parabola, 5/2. And you take it transversal to this component. So the axis of this is transversal. Then you get the same way you get C2. And the statement is the following, that they have the same Alexander polynomial. And so the Alexander polynomial does not determine the combinatorics of the resolution. I must confess that this, in principle, this does not imply directly that it does not determine the topology of the corresponding knot. Because from topological point of view, they can be, and in fact, I don't know how to verify this. I suspect that this is, that they are topologically different, but I don't know how to verify this. But nevertheless, so these are the places these are some places when the Alexander polynomial, in this case, the Alexander polynomial in one variable, does not determine the combinatorial structure of the resolution, of the minimal and band resolution of the curve. And because of that, there are difficulties to claim that the corresponding knots, and very only knots in this case, or links in other cases, are different. Okay. So what is the general statement in this case? By the way, in this case, the Alexander polynomial, and this is the general feature for all algebraic links. Alexander polynomial for algebraic links are always in the form of so-called binomial form. It means that they consist of products and ratios of binomials of the form 1 minus t in some power. So they are always like that. Product of 1 minus t in the power m in the power sn, where when I write t underline and m underline, it means that they are multiple ones. So this means here I write t1 in the power m1, etc. Tk, tr, the number of variables being the number of components which I deleted here, tr in the power mr. So this is binomial of this form, and sm can be both positive or negative. So in one case it is the numerator, in the other case it's the denominator, and for algebraic links, at least for with so though algebraic this is Alexander polynomial, so in fact this is not Alexander polynomial for I equal to 2. This is Alexander polynomial. Alexander polynomial. This is the same, but what I want to tell to, yeah, but this is okay. So I have to correct my equation here, because I wrote not the Alexander polynomial, but what I wrote. So it means that so I told that for these two curves, the Alexander polynomial is like that: t12. 1 minus t in the power 18 divided by 1 minus t in the power 4, 1 minus t in the power 6, and 1 minus t in the power 9. But this is wrong because I forgot that this is not the Alexander polynomial, but so-called z function of the monodromy, which is much more convenient for several variables. And to have the Alexander polynomial, you have to nothing more. Not too far. So Alexander polynomial is this for both curves, and so the Alexander polynomial does not determine the resolution of these curves. Now, general statement about the E8 singularity, and that is about the algebraic links in the Poincare sphere. The general statement is the following: that suppose you consider curves C inside C0, gems of curves inside our singularity, the singularity of type E8, this singularity, such that after on the minimal resolution of the surface singularity, that is on this picture or here in the dual picture, the corresponding curve either does not intersect this component at a smooth point, so this point is not bad, doesn't intersect this point, this component at this part, or so doesn't, and D8 it means, or doesn't intersect D6 also at smooth point. These points are not dangerous. Either that or that. Suppose that we consider on the curves which on the reducible curves, so that all components are here are only, for example, we exclude this, they are to the left of this. Then the statement is that in this case, the Alexander polynomial completely determines the combinatorial structure of the resolution, and because of that determines the topology of the link or not if the link consists of one component. Okay. Now I want, this is a general statement about the movement. But as I told you, in principle, if the Alexander polynomial are the same, I don't know how to verify whether or not the corresponding links are topologically equivalent or topologically different. The projection is that they, if the resolution is different, then they are different. Okay, now I move to the next step. Now I want to consider other rational singularities. Moreover, I don't want to consider all rational singularities. There are somehow classifications there. Boring, but so-called rational double points. These are singularities which appeared in this terminology, rational double points. They were defined and determined by Turina, and she gave the list of these surface singularities. And later, Arnold found that these are just, they are related to so-called simple singularities of function gems. So these are so-called singularities AK, DK, E6, E6, E7, then this E8, which I mentioned just now. These ones. E8 I have discussed, and all others I can discuss them. I will discuss them just a little. Now start to discuss. The problem is that in some sense, the analog of the Alexander polynomial cannot be defined in the way in which it can be defined for a knot or for a link in the three sphere or in the Poincare sphere, because in this case the corresponding links, the corresponding manifolds K. So if S is of this type, excluding E8, as I told, then the corresponding link is a rational homologous sphere, but not a homologous sphere. It has homologous finite homologous in dimension 1. And because of that, the topological definition does not work. But there is somehow strange, it was initially a strange observation. I'll discuss this in a moment also. That the Alexander polynomial can be identified with another invariant, which is initially seems to be analytic, but appears to be topological, and at least for rational surface singularity, and coincides with the Alexander polynomial. And the construction is like that. That suppose that you have, I'll discuss it in C3, in C2, excuse me. So in the case when we consider a plane curve. So in C2 we consider a plane curve. This I started with, but in fact it works also for the E8 singularity. So for the Poincare sphere, but I will not simply repeat everything. It doesn't matter. The differences. There is no difference. So suppose that the curve C is reducible. It means that it is union of Ci for I from 1 to R. I told that I is the number of components. And now for each Ci, you can do the following. You can take its parameterization, that is uniformization. Phi I is a map from C0 to C I0, so which is 1 to 1. So it is isomorphism outside of this of 0, but at 0 it is, of course, there is a singularity. For example, if Ci was, say, if Ci was, for example, a semi-cubic parabola, X, x cubed minus y squared is equal to 0. And of course, this parameterization means x is equal to t. Tau. Tau in the squared and y is equal to tau. So we have uniformizations. Now for each function here, so if you have a function f in O C20, that is function, gem of function at the origin of C2, excuse me, you can define so-called certain valuation, namely, let it be Vi of f will be the following, which is either an integer number or infinity. You take f and take its composition with phi I. So then you get a function on tau, and this function starts from a certain term. So a tau in the power b. A is not equal to 0, plus etc. So this is the Taylor decomposition of this function. And then this v, which we take v of f, is nothing else but this number. If by chance this is simply identically 0 with this composition, this means that in fact phi I is in the 0 level set of f. Then there are no terms, and you simply say that Vi of f is equal to infinity. So this is, one can see that this is evaluation or pre-evaluation, because sometimes when one permits infinite values, it is called pre-evaluation, but doesn't matter. There are different terminology. Certain evaluation on the ring, so Vi maps O C20 to z greater or equal to 0 union infinity plus infinity, as I told you, there has to be a number. And after you have this number of these evaluations, you have V1, etc., VR, one can determine a certain filtration on the ring of functions here on this ring. Namely, let us J of U underlined. U underlined means U1. This multi-index filtration. U1, etc. Oh, U. Yeah, okay. UR, which belongs to, in principle, there is reason to write z is greater or equal than 0 in the power R, but probably in a moment, some means I prefer to delete this in some sense to number the filtration by elements with negative indices as well. So I define this as being like that. It is the set of functions in O C20 such that Vi of f is greater or equal than Ui for all I is equal to 1, etc. to R. So this is a filtration in the sense that if U prime is less or equal than U2 prime, less or equal means that each component is less or equal. So component wise, of course, the ordering on the lattice is not complete. So this implies that J of U2 prime is inside J of U prime. And in fact, for this filtration, if the filtration is one index filtration, there is no problem to define its Poincaré series. So suppose you have that R is equal to 1. Then you simply say that Poincaré series of this field of a filtration, it doesn't matter, is nothing else but sum for U from 0 to infinity. In negative values does not matter because these elements will be obviously will vanish. you take J. So you have filtration, one index filtration. It means that you have J of 0. Inside it, you have J of 1. Inside you have J of 2, etc. And you get write the following: U of U of U factorized by J of U minus 1. Take its dimension, which in this case is rather it is simply to understand that this can be either 0 or 1, nothing else can happen, and multiply by no, let it be t, okay, t in the power u, and then you get a certain series in t, the Poincaré series of this filtration. No, for example, for this guy, you get the following. What is J0? J0 means that whether there are functions with u with v, excuse me, there is only one v. So how do you compute it? You take a function, you put function f of xy, you put there 2, and instead of x you put to squared, instead of y you put to cubed, you get a series in principle. And you have to look where does the series start from. And what do you have? What is J0? There is function, of course, one unit, non-vanishing function, which has for which the valuation is equal to 0. Then you have there are no functions with valuation equal to 1, because if the free term disappears, then there must be at least 2 squared. So you get J1 is equal in fact to J0. But then after that, you have in fact there is J2, which is strictly inside it. I can write it like that, because you have function which is G1. Just a moment. G1. Oh yes, of course. There is a function which is, but then you have exactly G3, no, and so on. There are strict inclusions after that. This is equal to that. And the Poincaré series is 1 plus tau squared, because when you want to factorize this by I made a mistake. Minus 1 is bigger. No, of course, this doesn't matter. You get this series, and this is the one can see that this is 1 minus t6 divided by 1 minus t cubed times 1 minus t squared. And this is in fact not the Poincaré, not the Alexander polynomial, but if you multiply by 1 minus t, you get the Alexander polynomial of the threefold. This is, and the statement is the following: that this way, so up to this multiple, which is simply different. This is nothing else but the Alexander polynomial in one variable of a node. However, if there are several components, the situation becomes much more complicated. Okay, much more complicated in the following sense. So when is my how many minutes do I have? 6. So then the situation is much more complicated in the following way, that even to find the formula for the Poincaré series, it is some sort of art, I would say. So when we with my courses discussed this, they told, the Poincaré series should be defined in the following way. Suppose you have a multi-index filtration, like this one, J of. Then you have to define the Poincaré series by the following formula, T1, etc. R, that's TR, is product, so sum of, you have to take the dimension, like here somehow, dimension of J of U factorized by J. Okay, U is a multi-index now. I told you that U is U1, etc. UR. Factorized by J of U plus 1. 1 means 1, 1, 1, 1. You take the element there. Take its dimension and sum up. So sum up only over all U. In fact, one wants, and for me it was a miracle, to write that this should be in Z greater or equal than 0 in the power. But no, one should take this one. So one should permit negative elements with negative exponents as well. And then one, this is somehow lies, I don't know where, because it is not a ring, not a model, but then you have to multiply by product of Ti minus 1 and divide by T1, etc. Tr minus 1. So when they suggested me this equation, I told that this was crazy, it's nonsense, I don't understand it. But after some computations, I was convinced that this is really the case. And the statement was the following, that in this case, for example, in C3, also in the E8 singularity later, which means then the result is nothing else but the Alexander polynomial of the corresponding algebraic link. If you take the intersection, then this is Alexander polynomial of this. In fact, this is a strange statement, whatever it means. So, nevertheless, this is a very strange statement in the following sense: that there is no conceptual proof of it up to now. Though this is a relatively old result, 20 years old, nevertheless, even in dimension 1, which was there, I mean, the number of components is 1. There is no conceptual proof. Namely, there is the result is obtained in the following way. One can compute this in terms of a resolution. One can compute this also in terms of a resolution. There is a equation which one can find in the book of Alexander Polynomial. And then you see that the result is the same. However, nobody succeeded to find why they are the same. But in fact, there is another way. One can write that this is integral another way that somehow justifies that this equation makes some sense. Of the following expression, V of F, the Euler characteristic, here is the integral with respect to the Euler characteristic in the sense of Vero, which I cannot discuss in details, over the set of productivization of the ring of function on C2. Or in the other way, on the set of divisors, this is the same, divisors. But in this case, in the case I have to finish, and because of that, it is a pity. I'll tell only that there are some, okay, concluding remarks, that in the case of C2, or in the case of the E8 singularity, which gives the Poincare sphere, the set of divisors, where you can write here, set of divisors, set of all divisors, singularity. All divisors are wild divisors. That means that they are defined by functions. But on other rational surface singularities, this is not the case. Wild divisors and Cartier divisors are different. And in order to get a reasonable substitute of the Poincare series of the Alexander polynomial, one has to integrate over the wild divisors, the set of wild divisors on the surface. And then the expression for the Poincare series will be of the same spirit with binomials. And the statement is the following, that I told that then if you consider this wild Poincare series, then for AI, Di, of course, if you consider singularity, for example, Di, you cannot distinguish between these two parts. So there is the answer is up to this, of course, involution. If you consider D4, then there is up to all exceptions. So D8, D6, and D7. That the statement is the following: that this while Poincare series, which is substitute of the Alexander Polynomial, determines the topology of the resolution for all these singularities completely. It determines the combinatorial type, and because of that determines the topology of the corresponding algebraic link. But for E7, there is the same, similar statement like for E8. Namely, there are two components of the 1, 2, 3, 4. One should take either curves which don't intersect this component or curves which don't intersect this component. And if you consider only them, then the while Poincare series, which is considered as a substitute of the Alexander Polynomial, completely determines the topology of the corresponding curve. Excuse me for shrinking the end of the talk a little, not a little bit, but considerably. But nevertheless, I have to finish. Thank you very much.
Questions?
Можно спросить, вот эта формула самая верхняя на правой доске, вот справа стоит полином, как я понял, Александра, а слева ряд Poincare. А почему все-таки полином равен ряду? Это потому что ряд конечный или это мистика?
Нет, этот ряд, конечно, бесконечный.
Ну так
Ряд
получается.
бесконечный. Но после этих умножений он становится, да?
То есть нет доказать, нет объяснения рационального, почему здесь нет хвоста, да? Это так результат вычисления такой.
Да, я, так сказать, ну, грубо говоря, если взять, даже я, например, говорю, что вот это вот обобщение на произвольные рациональные особенности, я даже не уверен, что всегда многочлен. Для этих многочлен, для double points. А дальше это, как я сказал, там беда в том, что вот, например, там такой есть математик Клосс Собак, когда я ему рассказал вот самый первый факт, одну переменную, сказал, ерунда, завтра я тебе принесу доказательства, нормальные, без всяких вычислений. Это было на конференции в какой-то понедельник. Во вторник я спрашиваю, принес? Ой, знаешь, я занят был, нет, завтра, в пятницу сказал, нет, не могу. И вот с тех пор 20 лет. Ну и поэтому и здесь я, да, это действительно многочисленно.
Okay, some more questions?
Thank you for interesting talk. And I would like to know, for classical mode for link, we can define a group, which is fundamental group of complementary, sphere, and so on. And if we consider algebraically, is it possible to define some group? And if it's possible, is it correct that this group is the same as in the classical?
What do you mean define a group? I mean, there is no. I don't see another group except the classical one. In some sense, for algebraic links, I don't see another. I don't see another links. These are particular links, but the group I don't see another
link is a classical.
I don't understand. This algebraic link is a particular case of link, and I don't see another group which can be different.
If you can define the same.
I only see the standard definition. I don't see another one which will give something different.
No, but maybe you.
No, yeah, maybe, but I don't see.
Only this.
I don't. Maybe this is can be a good question, but I never thought that there is some sort of algebraic analog which is different from the classical.
More questions? Zoom questions?
Zoom problems.
Okay, if you have no question, let us thank speaker again.